In this video, I want to show you how a computer program is transformed into something understandable by the computer. Here we have an example. This is a program written in C programming language. It doesn't do anything useful. It only assigns some values to some variables, performs an addition, and returns something. Uh, just I used those numbers just to be able to find the location of our program easily, more easily later. So this code, the computer can't execute this code because remember the computer has some instructions depending on the processor at a lower level. So before executing this program, we need to transform it into machine code. Okay, we need to transform this to the binary representation of the instructions a processor can execute. And once we have this, we need to load this into memory, and the processor could start executing it. So the first step, we're going to perform the first step, and is transform this program in machine code. So we will do it executing this. You don't need to remember this. And now we have two files. This is the original one with the source code, and this one is the one that the computer will be able to understand and execute. With the help of the operating system, we will see it in the next unit. So this is an ELF. This is an executable. It's a format for executable files, and you don't need to know the details of this format. But here we have transformed the source code into some format containing the instructions the computer can execute. And I'm going to show the contents of this file. I'm going to see the contents here with this other utility. And this is the program once compiled. And here, if we take a look at this, we can see that here is the instructions that corresponds to our source code. Okay, this is it's easily to see because we have these numbers here, the same that appear in the source code. Remember, this is the source code, and this is the compiled code. Okay, so it has been transformed to this kind of instructions. Okay, you see you have a push, a mob, a mobile, add, pop, red queue. So these instructions belongs to the X64. I think that it's called EMD64 computer architecture. This is the chip I have, and it's transformed. So this chip understands uh, uh, this this these instructions, and those are the operands of each instructions. Okay, in this case, it's doing something. I don't know what is this. It's storing this for recovering it later, using this just for accessing memory and so on. You don't need to understand it. Okay, but uh, these instructions, the processor is able to execute this directly. Okay, but this instruction is stored in memory using this binary number. This is a X because if not, it will be very, very long. So this is the representation that will be stored in memory before executing the program. So we have transformed this is the original code, into these binary numbers that will be stored in the memory and executed directly by the processor. Without this step, the processor won't be able to execute our program. So when you are programming, if you are compiling your program, not using an interpreted language, that it has a completely different way of work, but at the end you are executing this. So you're loading some bits into memory and the processor will execute it. So if we take a look at the contents of the file, Okay, this one. Okay, this is the file with the hexadecimal editor we have used before, and inside this file we can find this, our code. So these instructions. Okay, sorry, I don't know what I did. If I search for this string here, you can see our program is here. Here are the bits corresponding to our program. This is the first instruction, F3, 0F, 1A. Okay. The second instruction is F55. I think it's here, and so on and so forth. So we have, remember, source code. It has been compiled to some matching code, and it corresponds to bits that will be stored in memory. And but this is for one kind of computer. So these instructions are for one computer architecture. In this case, for the EMD64. But I can take the same source code and compile it to a different processor, and it will have a different set of instructions and a different representation in memory. So in this case, I'm going to compile it to an ERM architecture. ERM is the architecture that is usually used in mobile phones and on low consumption computers. And if I take a look at the contents, okay, this is the compiled code, but for a different processor. And here, somewhere, okay, here is our program. This pair, okay, you see the main. I think the other one has a main label too, right? The main label. And here is the same program compiled for a different processor. And as you can see, this is different, completely different for this architecture. So we have a different instruction set. We have STR, MOB, LDR, ADD. We have a different representation on this. This will correspond to the binary representation of this instruction, but it's the same program. The same program. If we execute this in in an ARM64 processor, it will do the same as if we execute this in a AMD 64. Okay, it's the same program, but it's different CPU, different instruction set, and different representation. And in this case, if we look for this into the file, okay, edit, I think was ART64, and we are looking for D10043. If I search for that, it won't be found. It won't be found. Why? Because the representation in memory is different. For example, in this case, we'll need to find if 43. So if 43, okay, and this is our program here. If 43 is reversed because it's stored the information in a different way in the memory, and it depends on the processor. So you can see here that at the end, what computers are executing are different instructions depending on the architecture. This kind of chip has these instructions. This chip has this instruction, and at the end they are binary bits that are stored in memory and read from the memory and execute from there.